before we begin verifying members, I thought I would show you a vision of what steel is like in the UK. I know that this will not necessarily reflect experience in your own country, but it may help you to understand some of my background and some of the views that I have about connections, about beams, about columns, about brace solutions. Because 70% of multi-storey buildings in the United Kingdom are steel. It would probably be the first choice solution. So, multi-storey, braced frames, composite floors. And in the UK, a number of different solutions have been investigated, and you will see the different prices on the screen. You might say, of course, the steel industry of course, the steel industry will say their solution is cheaper. In the UK, the concrete industry would do the same study, and they would say that their solution is cheaper. But we know best. If I was trying to sell a steel solution compared to a concrete solution, I would never try and provide an equivalent. So my understanding is that concrete solutions perhaps have a grid of 7 metres, 7.5 metres, maybe 8 metres, maybe even 9 metres. Sometimes people say, I will provide you a steel solution and that has a grid exactly identical to the concrete solution. 7 metres, 7.5 metres, 9 metres. And I would say, why would you possibly sell that as a solution? I would be selling long span solutions and saying I can provide you more space without columns in so that you can do whatever you like with your space. You can change your space when your building use changes, and my columns are rather smaller than your concrete equivalent. So I would never be trying to say a 9-metre solution in steel. I would be saying a 12-metre solution in steel, or a 15-metre solution in steel, or an 18-metre solution in steel. Smaller columns, less columns. So I would never try and compete directly with a concrete solution. I would also say that because a steel solution is lighter, the permanent actions mean that the loads on the foundations are less, and therefore smaller foundations are possible. And in some parts of the world that makes no difference whatsoever because rock is very close to the surface. But in some parts of the world, the fact that the foundations are smaller can be very attractive. Less cost, faster would be the solutions that I was trying to sell. Faster construction would mean that for some people, they can rent the building earlier, so they can start to get income from their rental. Smaller columns mean that they have a greater floor area to rent, and even though the difference perhaps is small, sometimes developers find the increase in lettable area to be very attractive. This would be the absolute standard solution in the UK. It would be a composite floor. So there is profiled steel sheeting, but the profiled steel sheeting has got indentations, which means that it is acting compositely with the concrete. So this slab typically might be 130 millimetres deep, so 130 millimetres from the bottom of the trough. We have another accidental action. Oh no, we don't. So 130 millimetres deep, probably with some mesh. This would be the cheapest solution, where the beam is simply, we call this a downstand beam. It just means that the beam is below the slab. The top surface of that beam will be unpainted, and it would be absolutely standard in the UK to do what is known as through-deck welding. So these shear studs, which are 100 millimetres long and 19 millimetres diameter, I don't know why they are 19 millimetres, but they always are 19 millimetres. These are welded through the deck onto the top surface of the beam. So the beam is unpainted. We're welding directly through the galvanised surface here, and we are very content that a good weld is produced. So we test these by hitting them with a hammer, or we get a very large pole which might be used for scaffolding, and we bend them to demonstrate that this weld is good. So this would be very, very common solution. If the structure is low-rise, so low-rise to me is perhaps 3 or 4 stories, no more than 3 or 4 stories, it would be relatively common to use precast concrete planks. So the precast concrete planks might span 7 metres, that sort of order, and they would be around about 200, 250 millimetres deep. And they would generally be hollow, so there will be cores running all the way through these precast planks. Occasionally, we would make the precast planks act compositely with the steel beam. So here is a solution where shear studs have been welded to the top of the steel beam in the fabrication workshop. There is a profiled or tapered end to each one of the concrete planks, and you'll see that the top surface has been broken out, and we will lay a reinforcing bar in each one of those slots, and then this area will be completed with in situ concrete. Always in the UK, construction depth is very important. So construction depth would be from the underside of the ceiling to the top of the carpet. So within that depth there would be the ceiling, there would be perhaps some air conditioning and some services, there would be the steelwork, there would be the slab, and maybe there would be a floor on top of the slab. So in order to reduce the construction depth to a minimum, in the UK, integrated solutions would be very common. So this is a cellular beam. I would imagine that you are familiar with those. There are regular circular openings. It would be very common for us to have a cellular beam, as you can see in this photo, with a composite slab on top. So the cellular beams are made by cutting a universal section, but then we would reassemble a lightweight top section and a heavyweight bottom section. Because the compression is being carried by the concrete slab, so the top section of the steel beam only needs to be lightweight. The tension is being carried by the steel beam, so the bottom section can be heavyweight. That would be a very common solution. And this has these openings so that you can put the services through them. This is also a very familiar solution. These are members fabricated from plate. So bottom flange, web and a top flange, all made from plate. Any sort of arrangement of holes, again, to pass the services through. You see in this case, quite a long opening, so the opening is being reinforced with strengtheners top and bottom. So those would be very familiar solutions. This might span 15 metres, maybe even more. So I would not even begin to think about 9 metres. I would be going 12, 15, 18, maybe 21 metres. That would be not unusual. And those would be spaced at approximately 3 meters or 3.5 meters, because the standard composite slab profile can easily span about 3.5 meters. So typical floor layouts for me would have secondary beams. In this case they're spanning 15 meters, and they're spanning onto primary beams, which in this case are spanning 7.5 meters. So a 7.5 meter by 15 meter grid would be very orthodox in the United Kingdom. Stability in the United Kingdom would almost always be by bracing. So here is some bracing. These would be steel diagonal members, and the diagonal members in the United Kingdom might be channel sections. I think you call them C-sections, or more often they would be hollow sections, maybe circular hollow sections or rectangular hollow sections, and they would work both in tension or compression, so they would be designed for compression. Everywhere else, it will be assumed that these connections are nominal pins, so the beams would be designed as simply supported. It would be very unusual for us to put moment connections between beams and columns, because we believe that moment connections are very expensive. So we would do very ordinary, very simple connections. Sometimes the stability is not provided by steel bracing, but would be provided by a concrete core. So for taller buildings, a concrete core, maybe the lifts will run up and down the concrete core. That will be equally as common in the UK. So these would be very common details that we would find. You've seen this diagram before, so a splice detail. The splices typically would be 1 meter above the floor level. This would be a very ordinary base for us. So these bolts are cast into cones so that we can move the bolts around to get a little bit of tolerance when the steel is placed on top of this foundation. Even though the base is extended outside the perimeter of the steel section, we would still class that as a nominally pinned base. So we would assume that that takes no moment. You might find that interesting because it clearly can carry some moment, but we assume it carries no moment. If we were going to design a moment-resisting base, the only difference would be that the base plate would be thicker. It would look just the same, except a thicker base plate. These would be very ordinary beam-to-column connections. So this is, we would call that a partial depth end plate. So our partial depth end plates are at least 60% of the depth of the beam, as a minimum. 60% of the depth of the beam, but it probably is not connected to the top flange or the bottom flange. It's only welded onto the web. And we consider that to be a nominally pinned connection. The other very common connection that we do would be a fin plate. So a plate coming out from the column and simply bolted through the web of the beam. And again, the fin plate would be a minimum 60% of the beam depth. In the UK, it would be 100% common practice for the steelwork fabricator to design the connections. Structural engineers simply choose the members. They would provide the shear reactions at the ends of the beams, and the steelwork contractors would detail those connections. So it would be for the steelwork contractor to decide if they are using end plate connections or fin plate connections. Most steelwork fabricators would use a three-dimensional drawing software. So they would have a three-dimensional model in the software, and that software would produce all the fabrication drawings and would produce all the data which the machinery then uses. So in a modern fabricator in the UK, nobody is doing any marking out by hand. It's all done by machine. Drilling holes, cutting plates, cutting beams, notching beams is all done by numerically controlled machinery. Fire protection, I think, is an issue here in the Ukraine. 75% of the steelwork in the UK would be intumescent coating. So an intumescent coating is a coating that, on exposure to heat, expands and then protects the steelwork. So this would be a very, very common solution. And I believe it's a lot cheaper in the UK because there are more companies who provide this sort of coating. So there is lots of competition, whereas I understand in the Ukraine it is not the same. So I hope that explains my background and the sort of solutions that I would look for in steel. My encouragement to you would to avoid trying to repeat a concrete scheme. What's the point of repeating a concrete scheme? I would suggest that you should always be looking for longer spans and be selling the advantages of steel, which is long spans, less columns, more adaptability, cheaper foundations, faster construction.